Fine. So today we start one of the most important part of the subject. Which is the Landau theory of continuous phase transitions. As I already briefly mentioned, this is basically sort of mean field theory. But this is a kind of theory which doesn't address the behavior of the system in any range of changing variables or like temperature or pressure. Instead, Landau concentrated on the vicinity of the phase transition. In other words, if we introduce, in fact, the only existing small parameter in any substance, which for any substance undergoing a continuous phase transition, in any attempt to describe it, you face a major difficulty. It's very hard to introduce any small parameter, except for this one. This is the deviation of, say, the temperature from its critical value, and the vicinity of phase transition is determined by this condition, that you are close enough to this point. And the only measure is Tc itself. So the deviation from Tc should be small as compared to Tc itself. Well, perhaps the most important achievement of Landau was not simply a description of the vicinity of the phase transition in terms of all the parameters of which you're already aware, such as magnetization or maybe a difference between the densities and the vapor-gas transition, or say macroscopic wave function for a system undergoing a superconducting transition and so forth and so on. The main message his message was the role of symmetry. You know, big people think in terms of big problems. Not tiny details, but very general, very basic notion of a symmetry. It can be easily understood if you look at the substance, the magnetic substance which undergoes a transition, say, which consists in the ordering of the constituent spins of magnetic moments, like a ferromagnetism, for instance. So suppose you are at temperatures which are above Tc, and you are basically in a ferromagnetic phase, which means that the average magnetization is 0. Right? Now if you recall where you started from, and you started from the expression of the Hamiltonian, which was fully symmetric with respect to any global rotations of the spins, right? So you have these elementary objects you're dealing with. These are the spins, or the magnetic moments, which undergo, there is an interaction between them, and we can write it down in this form, in the most familiar form, right? So let it be SR dot SR prime. These vectors may be classical or quantum spins, doesn't matter. Then what matters is there is a scalar product here. So therefore, you can imagine that we have a rotation matrix which belongs to this symmetry group. the usual orthogonal matrix, right, such that S alpha goes to S alpha prime, which is R alpha beta, and is beta. I can put R here and R here. If I say that this matrix does not depend on R, it means that if I rotate all the spins in the same fashion, then the scalar product will remain invariant. So how do you visualize the rotation in the three-dimensional space? Well, first of all, you choose the rotation axis. You call it n. N is a unit vector. Then you build up somewhere a plane which is perpendicular to this vector. In other words, this vector n is a normal vector with respect to this plane. And then you simply consider a finite rotation by angle omega. So you need two quantities, the rotation axis n and the rotation angle. The arbitrariness consists not only in the magnitude of omega, which can be any from 0 to 2 pi, but also there is an arbitrariness in the choice of the rotation axis. You can rotate around any axis. And this is what is meant full rotation group. Full symmetry group is SO3, orthogonal group. So this is the symmetry of your interaction. This is the symmetry of your Hamiltonian. And then you look at this. This is the order parameter, or the average magnetization, or the average magnetization, let me recall. This is sum over all the spins per unit volume. Say per unit, or maybe per the number of particles, per particle, that doesn't matter. This is the average magnetization in this paramagnetic phase. It is 0, that means that the speeds are completely chaotic, and there is no preferred direction in the spin space. In other words, the thermodynamically stable state, the solid state, is the high energy state, the high symmetry state, which shares the same symmetry as the symmetry of interaction. The symmetry of your Hamiltonian remains unbroken. If you are in the quantum regime, you would say, okay, I have a quantum Hamiltonian, I calculate the spectrum of this Hamiltonian, I find out that the ground state shares the same symmetry as the symmetry of the Hamiltonian. No miracle. This is the most frequent thing which happens in physics at all, in general. This is what happens in paraphase. But there is another phase, the low temperature phase. So if I lower the temperature and I curve below Tc, that I know, then the average magnetization now is non-zero. So what is the symmetry of this thing? If I know the direction of the spontaneous non-zero magnetization, here I choose it to look along some imaginary z-axis. I call this axis z. It may be any. It's up to you to choose it and to call it, however you call it, right? So if this direction and the magnitude of this vector determines the stable phase, the only symmetry which this phase possesses is the symmetry related to rotations around this axis. And this is already the much simpler orthogonal group. It's SO2. It's standard planar rotation. So you have a planar geometry, as you have learned at school, and you know how you rotate your vectors. It's the standard rotation rules in 2 dimensions. So the symmetry of the solid phase which was SO3, breaks down to symmetry SO2. And SO2 is a lower symmetry because it only allows you to rotate around the fixed axis. You cannot rotate around any other direction. Suppose this one, because M will start rotating, and then you're changing the ground state. You are forbidden to do so. The system has already chosen its ordered state, right? So the stable phase does not share the same symmetry with the Hamiltonian, with the free energy, for instance, right? Hamiltonian free energy, it's just equivalent notions. It becomes lower. That was one of the most important observations by Landau. And it will play a very significant role in what follows. There are many more examples. For instance, it's harder to perceive immediately, but maybe you will have a course on, of course you will. You will have a course with Professor Kiselev on many-volume physics. And there you will learn about the phenomena of superfluidity, for instance, or superconductivity. These are the quantum states of many particle, many electron systems, which are characterized by a macroscopic wave function. The wave function which characterizes not a behavior of a single particle, but the behavior of the whole, even though the wave function does depend on a single coordinate, generally speaking. It's a very generalized notion of some collective feature which is present in the system below the transition temperature, below the temperature of a transition to a superconducting or superfluid state. Right? Necessarily, this wave function has to be complex, which means that it is characterized by the absolute value or by the modulus here and by a phase. Why do you need this complexity? The reason is that what is written here is proportional to the square root of the so-called superfluid density. So not all electrons or not all the atoms in liquid helium undergo a transition. It happens like a Bose condensation. You will also learn in detail what is that. Part of the particles go to the condensate, but not all of them. All of them may not be present in the condensate, even at zero temperature, due to the interactions. But for us, it's important there is a certain fraction of particles, denoted by a rho sub s, as superfluid or superconducting, which occur in the condensate. And the wave function, its modulus, its absolute value, measure this amount, this quantity. But on top of that, you need a phase. Why do you need a phase? You need a phase because the velocity has to be proportional to the gradient of this phase. You perhaps remember from the course of quantum mechanics that it is impossible to define a current operator for a real wave function. If the wave function is real, like a wave function of an electron in a potential way, you can almost make it real because the Hamiltonian is real and the Schrödinger equation turns out to be easily solvable and the wave function can be real. There is no current in this case. The wave function describes a localized state just inside the wire. If you want to create, if you want to describe a quasi-particle or a particle which carries the mass and the charge and the spin, all the quantum numbers are attached to this particle, you have to deal with the wave function which is complex. You remember perhaps the definition, right? The current was in quantum mechanics was defined, I skip all the coefficients, it's imaginary height, and then basically what I have is psi conjugate gradient of psi minus complex value. If psi is real, the right-hand side vanishes. In other words, if I substitute psi in this form, eventually I will arrive to this. Because it's clear that the velocity has to be directly proportional or connected to the current by physical definition. So this is why this object has to be complex. Now the good question would be, if I have a system of particles with quantum mechanics, and it turns out that the symmetry of this Hamiltonian is such that the Hamiltonian is absolutely insensitive whether I choose the phase like this or I make a shift by a constant value omega phi naught, not depending on the coordinates. If I simply make a translation, global translation of the phase of this I don't call it all the parameters so far, not the field, macroscopic wave function, at any point by the same amount. There is a deep theorem which goes back to Noether. Noether was a lady who was an excellent mathematician and mathematical physicist. And there is a theorem by Noether which states that if your Hamiltonian or Lagrangian, whether in classical physics or in quantum mechanics, is invariant under continuous transformations, some continuous transformations, this transformation is definitely continuous because phi naught can be any number from 0 to 2 pi. Right? Then there should exist a conserved quantity, a conserved integral, which is associated with this translation, with this continuous transformation. So conservation laws follow from the symmetry. You perhaps remember examples of this kind. Take a free space, take a particle. The free space is completely uniform. What is conserved in case of this particle? Of course, it's momentum. So conservation of momentum follows from the uniformity of free space. Follows from translational invariance. In fact, if you build up the operator of translation by a vector A, it would look like plus or minus, it depends on the condition, the momentum operator times A. So, the momentum operator P, which is minus IH, blah, blah, the gradient operator, is just the generator of translations. If you do the same with translation variance in time, you will be dealing with conservation, not of momentum, but the conjugate quantity. What is the conjugate? The quantity which is conjugate to time. It's energy. It's energy. Energy is conserved. If you have invariance with respect to rotations, what will be conserved? Angular momentum. Absolutely. Of course. So this is why you can show, and this is quite a general statement, not necessarily related to the physics theory of phase transitions, but quite a general statement. If you have a complex quantity psi, which describes a system of fermions or bosons or any other particles with some fancy statistics these days, this statistic can be any, especially if you are in 2 dimensions. And your basic objects, such as Hamiltonian or Lagrangian or action, are invariant with respect to the phase transformations, which go basically to psi alpha, alpha naught, phi naught. Well, accordingly, of course, the conjugate goes to this one. Then the quantity which is conserved is the integral psi conjugate psi. Particle number. Just particle number. Just the particle. This is what is conserved. So therefore, in the normal phase, when you are in metallic phase, metal, typical metal, all these properties are well known, is expected to, due to some special features, to undergo a superconducting transition. So in the normal phase, the particle number is conserved. So therefore, this symmetry should be the symmetry of the ground state. As a consequence, you don't have any condensate, because a condensate is not invariant. Sure, a condensate is not invariant with respect to the phase shift. Condensate fixes the value of the wave function, therefore it fixes both the modulus and the phase. Then you go across the phase transition, you occur in a superfluid or a superconducting phase, where psi average is now 0. Consequently, the ground state chooses one of the allowed values of the phases, phi equal to 0, for instance, or some other value. It's a global value of the phase of the condensate. You cannot change it because it's fixed. You are in the state and you cannot, if you change it, then you will occur in the different state. Well, this symmetry, every time you have a complex quantity characterized by an angle phase, you can think in terms of planar geometry, two-dimensional geometry, and say the change of the phase is equivalent to a rotation of some vector. Because if you have a complex number, z, which is rho by phi, you can make a shift phi to phi plus phi naught, and from this you will simply show that x goes to x cosine phi naught plus y sine phi naught, and the same, and accordingly he will have minus sine phi naught and plus y cosine phi naught. What I want to say is just the change of his phase is nothing but the rotation of the two components of a complex quantity. A complex quantity consists of two parts. It's a real part, it's an imaginary part, and the real part, the imaginary part can be thought as the x and y coordinates on two-dimensional plane, as you perfectly know. So this rotation is spontaneously broken in the superfluid state. The phase is fixed. The number of particles is not concerned. There is a condensate of pairs of particles, bosons, and they can drop there without changing any energy. You can take out of that. I also don't change any energy. So this is a fancy property of it. Every time you break some symmetry, and this is why it has to do with, and this is why it is important from the point of view of Landau. Okay. This is one point. The second point, which is very important, is, so suppose I know all this, so I have to be consistent, I have to choose the symmetry which I will be dealing with, and the simplest version of that would be, why don't you start with the Z2 symmetry, with the discrete symmetry, which characterizes the so-called Ising model. All right, let us do that. Let us do that. So the symmetry should be Z2. We choose the only parameter. We call it M. The Z2 symmetry, I don't specify now anything. Landau himself would denote it not by M, but by eta. Sometimes in books and textbooks you find some more general definition. You label by different number. But for us, M is just, Ising magnetization. It's fair enough to keep it in mind like this. And due to this Z2 symmetry, inverting the sinus of M should have no effect whatsoever on the shape, on the fold, or the fringe. This is what Z2 invariance means, right? So this is quite a clear observation. But the second is then an assumption. The second thing is much deeper, as we already discussed. It's an assumption that the free energy, well, from now on, again, as last time, I will only deal with free energy either per particle or per unit volume. We will be dealing with the density of free energy, right? the free energy as a function of this order parameter. Well, one thing is clear. It should be an even function of M because of the Z2 invariance. But it could have been expanded in this form Please notice all of the terms are even functions of M. In cases I write down odd powers of the modulus of M, even in that case, I have a perfectly invariant expression for the free energy. This is not what Landau had in mind. There is such a possibility to have this kind of expansion, but it's a very special occasion. Maybe one day we'll discuss it as well. Landau completely eliminated terms like this and like this, because these terms break analyticity. So this function is a polynomial function of the modulus of M. Of course, is a continuous function, but it is not, generally speaking, an analytic function. Why? Because if you calculate the derivative of this function, here you have a modulus, and you nearly inevitably will have a jump discontinuity at the point m equal to 0 for the first derivative. And then you may observe the same for higher derivatives and so forth and so on. So therefore, this doesn't work. The assumption is that the free energy must be a continuous and analytic even function of M. So therefore, I can write down something like this. This is the value of this free energy at m equal to 0, or otherwise saying, if m is 0, therefore I'm in the solid phase, in high temperature phase. This is something which is not terribly interesting, right? So then you have an expansion in the standard form plus higher order terms. So let me write down M6. These terms I'm using. Well, if I want to add a magnetic field, I will add a term like this. I need to have such a term because I want to know the response of my system on some perturbation which directly couples to the other parameter. In the magnetic context, the system, the field which couples to the other parameter is nothing but the magnetic field. So therefore, to calculate susceptibilities, I need to have a magnetic field. To calculate in the magnetic field, to do all this calculation, in the end, they can send magnetic field down to 0. Yeah?
So one net with Z2 symmetry.
Well, we will break it right away. Yes. It will depend. Now I'm coming to this point. It depends on the sign of A. Yeah. So far, so good. Now, the good question is here to ask, I'm just trying to repeat again something which I already said last time. We insisted on saying that the continuous phase transition is a point of an essential singularity of the free energy. But you have to be careful. The singularity in terms of what? In which variables? Not in M. Somewhere here, there is a hidden information about the fact that the coefficients are the functions of this tau, which is the function of the temperature, and all other possible external parameters, such as pressure, if you wish. For us, it will be just sufficient to keep the pressure fixed. I'm saying all the other parameters fixed and deal only with tau, and the same with me. Generally speaking, if we continue this expression, all other coefficients must be functions. And continuous functions, analytic functions, because everything is analytic. Has to be. So how would you expect to find this essential singularity of this function at equilibrium when you approach the phase transition and send tau to 0. We have to find out the free energy, some coefficient, and tau in some fancy power, such that this dependence should clearly indicate that the point tau equal to 0, which is the critical point, is the point of essential singularity of this function. This cannot be analytic if lambda is, unless lambda is 2, or 4, or 6. Right? In any other cases, it's a non-analytic function. The answer goes as follows. That's actually the ambition, reflects the ambition of the theoreticians. What is the minimal input into the theory which is supposed to be able to describe phase transitions? We should not sacrifice the rigor and beauty and logic of the existing theory. We may expect some new features to emerge, not because we make our theory, looking ugly or unusual by introducing non-analytic pieces into the original expressions of the energy, high energy Hamiltonians or Lagrangians. Instead, we have to realize one important fact. Again, come back to basics. When phase transition can occur? What is the true conditions for the phase transition to be able to occur? You have to go to the thermodynamic limit. Otherwise, you have nothing. Because for any finite system, the free energy has been proven to be perfectly analytic, never giving you something like this. And there is no phase transition for any system whatsoever. Phase transition is a property of a thermodynamic limit only. The thermodynamic limit in turn means that you are dealing with infinite number of the degrees of freedom. Whereas everything you have learned so far had to do with finite systems. So it is new physics which emerges in objects which possess infinite number of degrees of freedom. So this infinity enforces F to look like this. In some very strange and not explicit way. You have to reveal it. But the input is just this one. Everything you start from is analytic. You end up in the thermodynamic limit at some kind of non-analyticity when you approach the critical point. Now, when you say, I have an infinite number of degrees of freedom, that means that I have an infinite number of particles, infinite volume, and only for such systems the correlation length may go to infinity. Because in a finite system, the correlation length cannot exceed the linear size of your object. Right? So therefore, it is the only quantity, the only meaningful physical quantity, which controls all peculiarities of the behavior of your system when the latter approaches the phase transition point. Everything is hidden here. If you know this, you know everything. That's the idea. Because this is the only control parameter which tells you what is the difference between finite and infinite. And you know that the phase transition is about infinite systems, not about finite systems. Okay. Well, having said that, now I should ask a very simple question. What should I expect regarding the shape of this free energy, which I should write down something like this. Suppose I set H equal to 0, I have no external magnetic field. I will measure delta F, which is F of M minus F naught, as a function of M. It's an even function given by these two terms. There are two cases. Number one, A is positive. If A is positive, then at small m, this term is the leading one. This is a small correction. Of course, so I have basically a parabolic dispersion at small m, which becomes steeper if I increased m. If this is a pure parabola, what I will observe, it will be something like this. The increase will be steeper. But of course, don't forget, everything applies to the region where magnetization is much less than 1. Okay, when I say much less than 1, I have to, of course, to think in terms of the density is magnetization per particle. All right? If I define m as the average value of the Ising variable, this quantity must be much less than 1. Right? So please make sure. So in other words, then magnetization, the one instead of what I had defined before, should have been defined as 1 over n sigma over r n sigma. Okay? For this expression, for such definition, I can safely assume this one. Otherwise, I will have a dimension. You know, you cannot say that the dimension full quantity is much less than 1. It cannot be. Only about dimensionless quantities you can say something, anything like this. Right? So let us assume, I will jump from one to the other up to my, it's a matter of convenience. Right? So this is a picture which tells you that you have a stable minimum at m equal to 0. B, the only thing which I didn't say, but of course I have assumed it, and I said it's steeper because I assume that B is positive. If B were negative, then it will be a disaster. It will go down at some larger value of B, right? I don't consider it. B is positive. If B is positive and A is positive, then this picture immediately tells me then the equilibrium value of M is 0. So what is written here is up to minimization, as you understand, right? It's a free energy for a non-equilibrium state characterized by a given value of M. Which specific value of M will indeed be realized follows from minimization of this free energy. Right? As usual. Now, second case. When A is negative, but B keeps being positive. Then instead of this maximum at small m, you have something like this. Because A is negative now. But you keep B positive. So at some point, B will take over and push the curve symmetrically upwards. You will end up with this kind of potential, which on top of the maximum at m equal to 0, it has two extra minima at plus minus m1. And you could calculate the location of these points. Now there is a remark and a problem for you to solve. By the way, I asked Signora Patricia and Signora Sandra to distribute the group with my lecture notes, something around Monday, Tuesday, next Monday, next. And there will be such a problem, but I can formulate the problem right away. Suppose that B is not positive. B is negative. What shall we do? Any suggestion? Suppose that in this expansion, B is negative. What shall we do?
Maybe take a higher from M6 term.
You are perfectly right. Yes. At least I have to add one more term. It will be plus D divided by, well, I'll call it 6. And to the 6, assuming that D is positive. If D is negative, then I have to go even further. Right? It may be very well that A more or less follows from A is allowed to take any values, positive and negative, B is negative, but then for this overall stability of the system, I have to have a sufficiently large values of magnetization, the coefficient which takes over with a positive coefficient. Right? Then you have to show, that's this here when the exercise, when the problem starts. You can write it down for yourself. Imagine that B is negative, so you add an extra term, the sixth order term, with a positive coefficient, presumably. And then how the picture of the free energy changes. How does it change? And what are the new features which emerge on top of what we can read off from this very simple picture? Right? So as you already know, this is the picture of the free energy for the second order phase transition. This phase is a paramagnetic phase, this phase is a ferromagnetic phase. And the condition is, and the transition is continuous. Because the transition point is A is equal to 0. So there should exist some value of tau such that at this value of tau, A goes to 0. We always are free to choose tau equal to 0. This is how you define TC. You will find out something new. I would like to see the way you think and what kind of conclusions you can arrive at. Right? So please solve it. Take this problem into account and try to solve it. So, as I said already, all these functions are expected to be analytic functions. And if this function is an analytic function, there is no one precludes me to choose Tc such that ATC is 0. If it is not, I can always make a corresponding redefinition of all the variables in the theory and achieve again arrive to this point. And then I will expand this quantity in small tau. Tau equal to 0 means that I'm just at Tc. At Tc it is 0, so the first term is alpha and tau itself. Plus higher order terms. Taylor expansion. The first nonlinear term is linear. The first non-zero term is linear, of course. So I see that alpha should be positive to have A positive. So therefore, A positive means that, in this case, tau is positive. This is for positive tau, which means T is greater than Tc. This is for negative tau. T is less than Tc. And that's the shape of the free energy, such that at criticality, here I have the dependence basically m to the fourth. This vanishes. It's almost flat. It's very, very, the curvature is large. And this, the shape is not parabolic, therefore the fluctuations are non-Gaussian. And that's the feature of these transitions. Well, this is basically it. Another thing is that in this specific case, as we already know, the discrete symmetry enforces all the levels to be discrete, and there is a finite gap between nearby levels. And this has to do with the discrete symmetry already, as I said. But there may be cases when the order parameter, when the symmetry, the original symmetry of the system is continuous. The same ferromagnetic moment, but not described by the Ising model, but instead described by the Heisenberg model with this kind of interaction. Here I have vectors, these are three-dimensional vectors, and therefore the broken symmetry phase would mean that if I now introduce a new quantity, let me, how to do it, and watch, as the average spin divided by its absolute area. Then this average spin will be defined on the two-dimensional sphere, and this is the one of the spontaneously broken directions. In this case, m is 0, 0, and not is just the equilibrium value of magnetization in the ordered phase. But if I had chosen any other direction, suppose this one, m prime, they will be as good as the original one. Because the only thing which I know that this full symmetry of the original system, which is the symmetry of the disordered phase, of the energy phase, has to do with full rotational group, as opposed to the Lorentz symmetry, which is SO2, planar rotations in the ordered phase. But I haven't specified the rotation axis. The rotation axis is determined by the spontaneous magnetization. Where should it look at? In which direction? It's up to your choice. Better to say it's up to the infinitesimally small applied magnetic field choice. You have to apply an infinitesimally small magnetic field to the system and force, suppose along z-axis. This is the direction of the field. If this field will enforce the magnetization to look along it, and then you switch it off, and it will remain. This is exactly how you break the symmetry. Because the system itself cannot break it. The only thing the system can tell you that any direction of the normal vector m on the sphere is equally fine. Any, right? In the case of Ising model, we have two such possibilities. All the spins up or all the spins down, and we cannot make a choice which one. The magnetic field helps us, right? The same we usually the same we do here, but the magnetic field in this case is not a scalar, it's a vector, which couples with magnetization levels. But otherwise saying it's just the same picture, the same physics. But there is something new, there is a novelty here. I cannot in an infinitesimally small fashion change the ground state, the minimal energy state in this case, because there are only two of them, either this or this. It's a discrete transformation. Either I have it, either I don't have it. Either I'm up or I'm down. There is nothing in between. Here there is something in between. I can consider a very, very closely oriented magnetization, which makes with the original one extremely small angle theta. I can do that. And then the good question is, what kind of motion of the spins would enforce the overall rotation of all the magnetic moments by a small angle? What kind of rotation it should be? What kind of motion it should be? Right? It's a very deep question. Maybe sometimes it's easier to understand what's going on if you recall the physics of lattice vibrations. In lattice vibrations, what we have suppose we have a one-dimensional system of equally spaced atoms. This distance is A0. And then we consider vibrations. And when we consider vibrations in case of such simple lattice, we know that in the long wavelength limit, when small k is small, when k times A naught is much less than 1, which means that the wavelength of this corresponding wave is much greater than A naught. Right? I have a linear dispersion. Omega of k is S modulus of k. These are the famous acoustic waves. All the layers, instead of modulus of k, you have sine of k not divided by 2 with some coefficient. The spectrum is finite, but a small k, you can linearize it, and you are right with this one. In other words, at small k, at large wavelengths, your system behaves as a string. The discreteness doesn't matter, because the wavelength is so large that the discreteness of the lattice at this limit doesn't play much role. You're effectively dealing with the string, with the elastic string. Right? Now, what is the motion which corresponds to the limit k equal to 0? What is that? Do you have any idea what kind of transition, what kind of motion? Suppose you have a finite sample. Okay, for a finite sample, I cannot literally send k to 0 because the minimal value of k will be 2 pi divided by the length of the system, as we all know, right? Compensation and laws. But nevertheless, imagine that you can consider the limit of finite but very long chain, or simply take it as infinite but take a little bit more imagination to figure out the right answer. What happens? Questions?
Center of mass.
Center of mass. Which center of mass of what? Of the unit cell? Or what?
Everything moves in phase.
Everything?
Moves in phase.
Everything moves in phase. What is that? When everything moves in the same fashion, what is that? How it's called? It's called translation. It's called the uniform rigid translation of the whole system. It moves as a whole. What is the change of energies in the limit of k equal to 0? It's 0. It doesn't take any energy. You know why it happens? Because your vibrating lattice is a lattice of atoms coupled by strings. It is only relative elastic forces play a role. None of these specific atoms is associated with some background like this. None of them is in its own potential well. There is no potential well at all. If you cut the strings, you have a system, a set of completely free atoms. Only elastic forces matter. So therefore, there is a mode when you simply rigidly translate your lattice, your sample, by some finite distance. It costs you nothing. And this is why we call these modes, the k equals 0 modes, the acoustic modes in the infinite wavelength, the Goldstone modes. This follows from the very deep theorem in quantum field theory and condensed. What is the analog? What is the counterpart for this? Instead of translations, here we have rotations. So we have to rotate all the spins, all the moments by an infinitesimally small angle. And I have to know the excitation energy. For ferromagnets, the excitation energy goes like this. It again goes to 0 when k goes to 0. It again costs me nothing. It costs me nothing if I rotate all the spins in the same fashion, absolutely in the same way. In other words, all the points here are simply degenerate. The transition from one point to another one is not associated with overcoming some potential barriers. There is none of it at all. No barriers at all. So therefore, the mode which wants to rotate This M is just the k equals 0 mode of a low energy excitation spectrum. These are the famous spin waves of magnons. Perhaps you will have them in the course of Professor Kissinger. And these are just the Goldstone modes, and the theorem claims that if you have a continuous symmetry which gets spontaneously broken, there should exist collective excitations of bosonic type whose spectrum goes to 0, whose energy goes to 0 in the infinite wavelength limit, and k goes to 0. What is the role of these excitations? You can see that if you are looking upwards and looking at the excitation at small k limit, that means that the system would like to change arbitrarily the direction of this magnetization arbitrarily and explore the whole surface of this two-dimensional sphere. If you are successful, then you have recovered your symmetry, the broken symmetry, right? So it's an interesting thing that you do have spontaneous breakdown of symmetry, but in case the symmetry is continuous, there are excitations which enforce magnetization to wander across this surface and effectively recover. There's a tendency of the system to recover the broken symmetry. This is impossible in case of the Ising model because there's a finite gap. Here omega goes to 0. Here omega goes to 0. Where is it? Here. But here omega does not goes to 0. Here omega is of the order of J. In case you have gaps, you are lost. There are no Goldstone modes.
Excuse me.
Yeah.
Sir, you said that symmetries can be recovered.
I'm not saying can be recovered. They can't. There is a collective mode. So in the ferromagnet, there should exist a collective mode who you can interpret the existence of this mode as the mode which tends to recover the broken symmetry. Because in the limit when omega goes to 0, the energy goes to 0, telling you that your original choice is not quite stable. It can be any. This is the only thing it does. The only thing it does. You should proceed in the following way. You should switch on again a magnetic field. You will lift this degeneracy. Your state will be the only non-degenerate state with the absolutely lowest energy state. And then, if you look at on the spectrum, it will acquire a gap and will resemble the Ising model. But in case I switch off the magnetic field, the gap will vanish, and I will recover everything I said about this picture. So, please don't perceive the phase transition as simple as the pendulum or any other mechanical problem. It's a very serious thing because it has to do with infinitely many degrees of freedom. Physics changes. As Phil Anderson said, the father of condensed matter physics, more is different. Every time you look at the systems with large degrees of freedom, large number of degrees of freedom, physics changes. You're not having anything like Goldstone mode in finite system. It's only the property of a field theoretical limit, infinite number of degrees of freedom.
Question.
Yeah.
So this Goldstone theorem, does it also give me does it also tell me whether can my spectrum be proportional to k cubed or k to the 4?
Well, that's a fantastically clever question. Thank you for asking me. It's very tricky. I think you already are under impression of this wrongly looking expression. So the Goldstone theorem, in the way it has been formulated, and it has been formulated, Jeffrey Goldstone was a high-energy physicist. Of course, he had in mind the situation with particle physics and quantum field theory. It is assumed that at low energies, the system, the Lagrangian or Hamiltonian or action, describing your system at very, very low energies, when you are close to the transition, such that you are considering the part of the spectrum not much different from the ground state one, right? So if you're interested in the distances which are much, much longer than the lattice spacing, then there is an extra requirement. You have to be a Lorentz invariant. You must be Lorentz invariant. Lattice vibrations give us such an example. Because if I go to the description of lattice vibrations, if uxt is the displacement field, you remember what the displacement field is? I write down the location of my atom in this chain as Na0 plus unt, when unt is a deviation from the equilibrium value, which is time dependent. In other words, I allow all the atoms to vibrate, to deviate from its equilibrium positions, right? And then I ask you what happens at low energies. And then what happens at low energies is the following thing. The effect if u and x transforms the field, first of all. Instead of n, I should write down x. And x is not the same as n, it's a coarse-grained coordinate, smooth coordinate. And the equation it satisfies looks as follows. It's 1 over s squared. The second derivative is a time derivative, minus d2 dx squared. uxt is equal to 0. It's a wave equation. Very simple wave equation. And you used to be happy with it for many years. You know it for very well. Did you realize that this equation possesses Lorentz invariance? Because the good question to ask would be, which quantity? So I have two coordinates. One coordinate is x, the other coordinate is also a coordinate this time. And I want to build up the length element out of these two coordinates, which stays invariant, so that this equation reflects this invariance. And this is how this element looks like. It's the famous interval in the Einstein's relativity theory, with the only difference that instead of the speed of light, c, I have the sound velocity. So this is not the true Lorentz invariance. This is not the Lorentz invariance, which implies that any of the existing excitations of condensed matter physics spread propagate in space with a huge velocity equal to c. No, the velocity is of the order of s, when s is the velocity, the sound velocity, which is many, many orders smaller. But the structure tells you it is not like in Euclidean matrix when you write down dl squared equals to dx squared plus dy squared. This is the length element in Euclidean two-dimensional space. And this is a super-Euclidean dimensional space. With the interval, this is invariant under Lorentz transformations, not the simple rotations, the boosts instead of rotations here. Right? As a consequence, omega squared omega cannot be a quadratic function of k. It should be a linear function because due to the symmetric way how the time and x enter, it should look like this. This follows directly from the structure, from the invariance of this interval. So you see, many things can be anticipated by very general principles. This is why in antiferromagnets I have something like this. But in ferromagnets I don't. And for that there is a deep symmetry reason. But I cannot now, if I keep discussing this issue, I will deviate completely from my plan. Maybe afterwards, or in private, or maybe at some other time, I will be eager to discuss it. All right, so there is some Lorentz invariance which enforces the spectrum to look not like this, but what like we have in case of forms. It should be a linear dispersion. Linear dispersion means that, in fact, omega squared is k squared. And that follows from the Lorentz invariance. All right, okay. Now a little bit more about thing which, as a matter of fact, the students don't like very much, but it's quite necessary to discuss at some point. Maybe lattice vibrations are good examples. A good example. If I have a lattice vibrations and I have a displacement field, and M tells me which displacement of which atom I'm having mind. Right? Now imagine that indeed your K is such that K times A naught is much less than 1. You're interested in the part of phase space characterized by small momentum, which means that according to the general properties of the Fourier transformation, according to the Heisenberg uncertainty principle, this means that the wavelength of corresponding excitation should be much greater than A naught. So the wavelength is large compared to the microscopic structure of the underlying lattice. So the lattice doesn't matter at all already. I can get rid of the lattice. How? The formal way would be, the formal mathematical way would be, if I have this as a discrete coordinate, I can pass to the continuum limit. I can pass from a discrete manifold to a continuous space by doing the following formal transformation. I should send n to infinity, A naught to 0, such that xn transforms to some x, which is finite. This is the mathematical prescription. Physicists are not always happy with this. A physical definition of the point x is different. If I have a chain, I know that vibration with k, which are small, means that if I have a displacement to the right, the neighboring atom will also have a displacement to the right, maybe the length of this vector, which tells me, gives me information about the modulus of u, will be a little bit smaller, smaller, nothing here, but here I can start moving in the opposite direction, increasing the displacement. So you see what happens? I have big groups, large groups of atoms moving almost with the same phase. Literally big objects, droplets of atoms moving as a whole with almost the same velocity, to the right and to the left. This motion almost excluded in this limit. This would be the case of an optical phonon. I'm talking about the acoustic phonons with small k. In other words, instead of looking at some point, I can average my displacement over some 1 over m star and divide by this n star and call it, and average it, and call it u of x. And the x is somewhere here, and this is the amount of sites involved. If n star is much greater than 1, but much less than the total number of particles, then I have defined a field already, which depends on the physical coordinate, which is not exactly simple, doesn't coincide with the latest sites. It includes many sites. Many in the sense that the number of these such sites are much greater than 1, but still this number is much less than the total number of lattice sites. This is what is called, what is known by the name of coarse-graining. You're passing to a rough picture, average picture, locally average picture. This is what x, contiguous x, means. Coordinate, which appears in the definition of the field, is exactly what I have shown you here. And you can do precisely the same here if you have some field. If you have a ferromagnet, whether it's an Ising ferromagnet or it's a Heisenberg ferromagnet, whether the symmetry is discrete or it is continuous, you can assume that you can divide your volume onto blocks of the length L star, such that L star divided by not this number, call it N star, which is much greater than 1. The corresponding volume would be L star to the power of D, when we use the dimensionality of space. And the condition is that N star is much bigger than 1, but it's be much less than some other number. What is that other number? The length of the system? Or the total particle number, number of spins? No. We are close to the transition. And the whole physics develops over the length, which is the correlation length. So therefore, I have to measure this correlation length in units of the fundamental spacing. And that will give me the number of spins involved in correlations. This is the physical process I must to keep and be able to describe in all the detail. What happens at shorter distance, I'm not much interested in the continuum limit. Therefore, I should impose this condition. This number must be greater than 1 to be able to average over this volume, but should be much less than the correlation length. In other words, L star must be much greater than A naught and much less than psi. This is a more transparent definition of what I'm trying to do. Now, within this smaller volume, I can introduce my x and replace mn by some vector m depending on x. Using some kind of definition very similar to what is written here. I don't want to write it again. It's the same. This is again what is called coarse-graining. And then my magnetic moment, or magnetization, becomes a local function of this x, such that I cannot ask the question what happens at distances of the order of A naught. This information is lost once and forever. But I can ask what happens at distances comparable to psi, to the correlation length. That makes sense. On top of that, all this will be consistent if the following condition is satisfied. Anyway, look carefully what it means. It's dimensionless. I already made it dimensionless. It means that the change of magnetization over the lattice site is very, very small. That means that the m of x is a very smooth function of the coordinate. It doesn't change very much. Why? Because it has been averaged. It's coarse-graining. There is no other way, because all the neighboring or short distance, the atoms which are located at shorter distances, move or rotate almost in phase. In this case, I'm using the language for the continuous SO3 model rather than the Ising one, because in the Ising one we have to keep this bookkeeping up, down, and then it's hard, it's slightly less transparent, but essentially the same. So therefore, the theory should be formulated in general case in terms of the magnetization. The theory should be formulated in terms of magnetization. Call it m alpha as a function of x, and its gradients d dx alpha and beta generally. So therefore, the free energy expansion should be up here as an integral form or a functional form, expanding powers of this object and this object with all respect of the underlying symmetries. The symmetry goes first, should be formulated, and all this expansion is subject to the symmetry restrictions. Yep. All right. So, these are just general things which we discussed. Now we can turn to, if you have any questions. Yeah. Yeah, please.
In the Landau expansion, is it sufficient to just look at the A and B to say that it's second order? Because can't you have it?
Well, if the sign of A is arbitrary and B is positive, that's the end of the story. Yeah, that's the end of the story.
But if both A and B are positive, can't it be that some higher order term would?
Very unlikely. You see, then you will again be facing a situation with the first order transition. The continuous transition are faithfully described by a free energy which is expanded up to fourth order terms, and that's the end of the story. All continuous transitions fall into this category. It's basically what I'm talking about, because the fourth order term is the simpler version of the free energy expansion, which gives you a non-zero result for spontaneous mobilization. And moreover, the spontaneous mobilization develops in a continuous way from zero, continuously grows lower. So, yes, the answer is generally yes. There is no such a restriction, or I'm exploiting all possible conditions which you impose on the theory to be most consistent, and most of them are simplicity. This is one. The theory must be as simple as possible. The second, all the symmetry aspects must be taken into account. This is the and that's exactly what is used. You can use the sixth order term, but please notice when I suggested you to explore this possibility. When I said that B may be negative. There are substances in B are not positive. I was witnessing it when I was younger that there were papers when expansion has been done out to 12th order, whatever. The authors would insist that it's important because of the specific features of some substance they were looking at and measuring. Yeah, it's possible. I can't exclude it, but it's not generic. It is not most general thing. The most general thing is this. That's the answer.
So, regarding this expression that you said that
This which one? This one?
No, sir, the gradient of M, the latest one. Yes, sir. You said that because now it only varies in a smaller fashion among the nearest neighbors. But sir, if we see at the model, let's, for example, if we look at just the Ising model, then just by looking at the Hamiltonian, the correlation is not introduced there. It can take any possibility, like it can be up or down.
Well, it's a good question. I got you. It's a very good question. The question is, if we have an Ising model where the spins are up and down, how can we ensure that in the coarse-graining description, the order parameter still varies in a very short manner at the minimal energy, minimal distance size? So how to reconcile the discreteness of the model with a small gradient? What is meant by the gradient when everything is discrete, both space and the change of the order parameter? So in other words, what you need to do is the following. Let me give an example. Let me choose some direction for the Ising model, this one. And let me put the lattice here. Imagine you have a configuration. All right. We have to choose how many sides we will take as a measure of a box. It's up to us. Right? Okay. I took this box. 3 spins in a box. The total M is 3 in this case, right? Another box. The total M is 1. Another box. Again, M is 1. Another box. Again, M is 1. One more box. M is minus 1. One more box. M is minus 1. M is minus 3. So you see, you go from 3 to 1 to 1 to 1 to minus 1, minus 1, minus 3. All right? And this is because we have chosen a box with 3 sides. Now choose a box with 4 sides. You'll find out many more and smaller, many more values of total box magnetizations, such that the difference would be smaller than it is here, relatively smaller. And if you choose them large enough, you will have something, say 16, you will have 16, then you will have 14, you will have 14, 16, again 14, maybe 10, and then you go to something like minus 2, minus 4, and so forth and so forth. So you see that what matters is not the fact that 16 minus 14 is 2, but the difference 16 minus 14 divided by 16, the relative one, is small. So you have to build up a histogram if you wish. And then you consider the relative values of the magnetization, which will of course be discrete because of the discreteness. The remark was absolutely correct. But I can always recast everything as a field with slowly varying in space. So you can convince yourself. Just play a game with this. Choose different boxes. For the smaller the box, the worse the result. That's for sure, right? For sufficiently large boxes, you can convince yourself. Yeah, so now we pass directly to the Landau expansion. First of all, the simplest version of the Landau expansion is the one in which fluctuations are completely neglected, which means that the order parameter is not allowed to be coordinate dependent, which means that in the free energy expansion, we don't have gradient terms at all. Then everything looks very simple. Our free energy, I will always subtract this F naught. I will simply write down the F of M and start with the standard term. Well, let me also do this. So this is the, as I said, a non-equilibrium expression for the free energy. In other words, it describes a possible state, a possible thermodynamic state of my system with a given value of M. But I have to figure out whether or not this state corresponds to the absolute minimum of the free energy. In other words, it's thermodynamically absolutely stable. Right? To do that, I calculate the first derivative, and I get AM plus B M cubed minus H, which is the same as M, FA plus BM squared minus H has to be equal to 0. Well, if the magnetic field is 0, if the magnetic field is 0, then we have an equation MA plus B M squared equal to 0. We have already had this expression when we considered the midfield theory of the azimuth. And you convince yourself that indeed the Landau theory is essentially a midfield theory, which is no surprise because I have dropped out not only strong fluctuations, but also I dropped out all possible fluctuations, including those which lead to non-uniform distributions of the other parameters. Very good. What we do next, we already have a shape for the free energy in this case. I will not do it anymore. The only thing is that I know that A is alpha tau times tau. Alpha is positive. So therefore I have two situations when tau is greater than 0. Then A is positive. This expression is positive. The only solution is n equal to 0. This is the disordered phase or power phase. And now there is tau less than 0. Keeping in mind the shape of the free energy, I have to drop the solution n equal to 0 because it doesn't correspond to a minimum, but corresponds to a rather to a maximum. But I have two solutions, m equal to plus minus m naught. A plus b m naught squared is equal to 0. In other words, m naught squared is minus a divided by b is alpha tau modulus divided by b. From which you conclude that m naught is proportional to square root of tau. That means that in the second order transition of the Ising-like model, if there is a TC, of course I am only restricted with some vicinity of this transition. I have 0 here, and of course I can extend it to any temperature, and here I have an increase, a singular increase of magnetization. This is a naught, which I can continue because I know the solution, mean field solution. This is a naught as a function of t, which has a square root singularity at tau equal to 0. So the first of all, analysis interface theory. Perfectly well-defined analytic expression leads you to non-analytic behavior of magnetization. The first observation. Now I have to apologize because last time when we were discussing briefly the behavior of the magnetization at criticality as a function of magnetic field, I wrote that it is a h to the power 1/8. You know, when you are dealing with a two-dimensional Ising model, and I've been dealing with this for the past 25 or 30 years, this 1/8 is so deeply memorized in your mind that even in case you have to write down 1/3, you automatically write 1/8, because 1/8 is the so-called scaling dimension of the strongly fluctuating order parameter field to the two-dimensional, not the mean field, but exact solution. I apologize. Now we will recover because we will now derive. Suppose we are at criticality. What it means? It means that tau is equal to 0. It means that A is equal to 0. Right? Tau is equal to 0, A is equal to 0. But now we have to switch to keep the magnetic field. I want to find out the dependence of magnetization on the magnetic field. I'm left with equation B m cubed is h, which means that m is proportional to h to the power not 1/8, but 1/3. I'm sorry about it. So you see how the magnetization behaves exactly at the critical point if you apply a weak magnetic field. There is no Curie law, as you can see. The Curie law would mean that the magnetization is proportional to h. It would be a first power. Here we have, again, non-analyticity. Well, to be quite honest, to be quite precise, I have to put here signature of h. The sign of magnetization must follow the sign of the magnet as well. Okay. So this, by the way, result tells us, gives us the value of one of the critical exponents the theory of phase transitions, this exponent which determines beta is in the mean field in Landau theory is just 1/2, as follows from here, and there is also m tau equal to 0, okay, h equal to 0, h equal to 0, tau equal to 0, h is proportional to h to the power 1 over the delta, and delta is 1/3. Is 3, because 1 over delta is 3. So already two indices for the mean field we already have. Now you can do the following, you can play the following game. You would like to know what is the magnetic susceptibility at the transition. Let me recall you that the magnetic susceptibility is defined as the derivative of magnetization with respect to magnetic field. This is the definition. Basically, we'll be interested in the behavior of susceptibility in zero field. So by the end of all the calculation, we'll send the magnetic field to 0, which means that in this way we will measure the intrinsic properties of the system itself in the absence of the magnetic field. So the magnetic field plays the role of the external probe. We make a test. We perturb the system, look at its response, and then we switch off this perturbation and measure what we have found. So, what measure the reaction of the system. Okay, so what do we do? How shall we do these calculations? It's very simple. We're looking at this equation. The first is A dm dh plus B 3 d m squared dm dh is equal to 1. I have differentiated this expression, this equation with respect to external magnetic field. So what I have is the susceptibility, dm dh is the susceptibility. Here I have A plus 3 d m squared is equal to 1. Above TC. Above TC, the average value of m is equal to 0. So the susceptibility goes 1 is 1 over A, which is 1 over alpha times tau. Below TC. Below TC, m naught squared is minus A divided by B. The result is minus 1 over 2A. A is negative, so therefore it is 1, 2 alpha tau modulus. So for the susceptibility, we have the following definition at the transition at zero field. It's tau to the power minus gamma, and in the mean field case, gamma is just simply 1. So this is the simplest things which can be done, extracted from the Landau mean field theory, which, as you can see, perfectly reproduce the mean field theory result, because simply identical. There is no difference. The only difference is that in the mean field theory, you don't assume that the temperature is very close to TC. The temperature is any. In Landau theory, it specifies the vicinity of the phase transition. Does it mean that this time is correct?
Yes.
So it's overdue already, right?
Yes, 5 minutes.
Oh, 5 minutes. Okay, so therefore, at this point, how do I switch it off? Pushing here?
Yes.